For several decades, software followed a familiar and predictable pattern, but that era is quietly ending. Right now, software systems are entering a new wave of transformation, one so significant that it's rewriting the foundations of how software works. The crazy part? Most people don't even realize it's happening. A lot of us are still learning, building, and thinking about software using old mental models. And whether you're a student, a developer, a designer, a founder, or simply someone curious about where the world is heading, understanding this shift matters. So, in this video, we're going to break down the current stage of software systems, how software used to work. Throughout most of modern computing history, software followed a linear path. Programmers wrote explicit instructions, and computers executed them step by step, much like a chef following a recipe exactly as written. This was deterministic software. Given a specific input, the outcome was always predictable, because every rule was defined in advance. The machine didn't understand what it was doing. It didn't reason, infer, or adapt. It simply obeyed. Developers had to anticipate everything: normal behavior, edge cases, failures, and exceptions. If something went wrong, the fix meant digging into the logic, finding the flaw, and rewriting the rules. New features required more code, stacked on top of existing code. This approach powered nearly everything we relied on for decades. Websites, mobile apps, operating systems, video games, enterprise software, and even banking and financial infrastructure were built this way. Its effectiveness was undeniable. But the model came with serious limitations. Software development demanded extreme precision. A single typo, a missing semicolon, or an unclosed bracket could crash an entire program. Computers did exactly what they were told, not what the programmer meant. This led to notorious failures like divide by zero errors, where machines blindly attempted impossible operations. As software grew larger and more ambitious, complexity exploded. Every new feature introduced more rules, more conditions, and more exceptions. Code bases became tangled webs of dependencies where a small change in one area could unexpectedly break something else. A problem often described as spaghetti code. To survive this growing fragility, entire ecosystems emerged around testing, debugging, version control, and code reviews. Despite its limitations, deterministic software thrived because of three powerful strengths: predictability, controllability, and verifiability. Engineers could reason logically about how a program would behave, trace errors back to specific lines of code, and in high-stakes fields like aerospace or medical devices, even mathematically prove correctness. This made deterministic systems trustworthy and safe in environments where failure was not an option. But there was an invisible ceiling to this paradigm. Some problems simply refused to fit into rigid, rule-based logic. Tasks involving natural language, vision, sound, or human behavior required an overwhelming number of conditional rules, and still fell short. This gap exposed the need for a fundamental shift. The first big shift: trained sorceress. Trained software. Instead of explicitly programming behavior, developers began experimenting with training it. Rather than telling a system how to recognize a face through rules, they fed it millions of labeled images and allowed it to discover patterns on its own. For language tasks, models were trained on vast collections of text, learning grammar, meaning, and context from examples instead of predefined syntax trees. This marked a complete inversion of the traditional software model. In traditional systems, code defined behavior and data was passive. In this new era of trained software, data became the architect of behavior, while code simply coordinated the learning process. The rise of trained software was powered by a perfect storm of breakthroughs. First came the data explosion of the internet age: billions of images from social platforms, trillions of words from books and websites, and endless streams of audio and video. Second, computing power became accessible. GPUs, originally designed for graphics, turned out to be ideal for parallel mathematical operations, making large-scale training feasible. Third, advances in algorithms, particularly deep neural networks and efficient backpropagation, enabled models to build layered representations of data. For the first time, machines became good at tasks humans found intuitive: recognizing faces, understanding speech, translating languages, detecting fraud, and recommending content. Yet trained software introduced new trade-offs. These systems were powerful, but rigid. Once trained, their internal parameters were effectively frozen. Changing behavior meant retraining the entire model. Worse, these models were opaque. Most importantly, early trained systems were narrow specialists. An image classifier couldn't understand speech. A recommendation model couldn't reason about medicine. Each system was trained for one task and one task only, with little ability to generalize beyond its domain. Still, the impact was undeniable. Trained software proved that machines could learn from experience, that behavior didn't need to be explicitly programmed, and that data could replace rules at scale. It shattered long-standing assumptions about what computers could do, and in doing so, laid the foundation for the next, even more radical evolution. The second shift, language as code. The next transformation didn't replace trained software, it was built directly on top of it. What changed was the interface. Language itself became the control layer. Instead of locking behavior inside frozen model weights, these systems learned to interpret human intent expressed in natural language. Rather than spelling out every step, rule, and edge case, users could simply describe what they wanted and the system would infer how to achieve it. The barrier of traditional programming syntax collapsed. Natural language became the universal code, instantly opening software creation and control to anyone who could clearly express a thought. Computers had accepted text input for decades, but this was fundamentally different. These systems didn't just parse keywords, they modeled language as a whole. They understood context, intent, tone, and nuance. They inferred constraints that were never explicitly stated. They maintained state across interactions. This shift reintroduced programmability to trained systems, but in a fluid, live form. Instead of baking behavior in advance, users could steer it dynamically. They can correct mistakes mid-task, refine goals on the fly, and change direction without restarting. Software moved from execution to collaboration. The workflow became iterative. The system proposed, the human refined, the system adjusted. This feedback loop unlocked massive gains in speed and creativity. But this evolution challenges deeply held assumptions. Traditional software earned trust by being exact, deterministic, and obedient. Language-based systems are none of those things. They are probabilistic. They generate responses based on patterns, not guarantees. They can sound confident while being wrong. They can reach correct answers through flawed reasoning. That duality is what makes these systems so powerful and so dangerous. Beyond tools, language models as operating systems. A common misconception is treating these systems as simple tools. Ask a question, get an answer, and move on. But that framing misses what they've quietly become. In practice, they function much more like full-fledged operating systems. They manage memory by retaining context across interactions. They decompose complex requests into smaller subtasks. They decide which capabilities to invoke. This perspective explains why these systems look the way they do today. They are resource-intensive and primarily cloud-based, resembling the time-sharing mainframes of the 1960s. Back then, computing power was scarce and expensive, so users accessed it remotely, sharing a centralized machine. Today's AI operates the same way. Inference runs on specialized hardware, costs are high, and access is metered through subscriptions or APIs. In that sense, we're living in the time-sharing era of AI. But history also tells us what comes next. Mainframes gave way to personal computers, and AI is on the same trajectory. Advances in model efficiency, compression, and specialized chips are already pushing intelligence onto personal devices. Smaller, optimized models can now run on smartphones, laptops, and edge devices, enabling on-device reasoning, privacy-preserving interactions, and always-available intelligence. Software must now serve AI too. Software is no longer built only for people. A new shift is happening. AI systems are becoming users of software just like humans. These AI agents can read APIs, understand documentation, and carry out actions on their own, but only if the software is designed for them. Old-style systems make this difficult. Things like CAPTCHAs, unclear buttons such as "click here," or messy, unstructured web pages confuse AI agents. These systems were built only for human eyes, not machine understanding. To prepare for the future, software needs to change. It should focus on clear, machine-readable formats like JSON APIs instead of scraped web pages, well-structured data with meaningful labels, direct, predictable endpoints, standards that allow AI tools to communicate and take actions safely, such as Model Context Protocol. New frameworks like AutoGen and Langflow already support systems where multiple AI agents work together. Platforms like Azure AI Foundry host models designed to interact smoothly with tools and other agents. What this means for the next decade. This shift toward autonomous collaborative AI will not happen overnight. It will be uneven and sometimes uncomfortable. There are real challenges ahead. Making sure AI systems behave ethically, managing high energy and infrastructure costs, creating fair regulations and equal access, reducing errors, hallucinations, and bias. These problems won't disappear immediately, but the overall direction is clear and irreversible. Those who focus on verification, smart system design, and human-AI teamwork will succeed. If handled wisely, this new era can unlock enormous creativity, discovery, and efficiency, amplifying what humans can achieve rather than replacing it. If you find this video insightful, make sure to like and subscribe for more updates on the AI landscape.